Hello everyone, and thank you for joining today. My name is Vishwanath Lanka, and today we're going to talk about LEAP, Axion's local extracellular action potential capability on the Maestro MEA platform. The focus of this talk is simple. How can we bring action potential-like insight into a scalable MEA workflow? Cardiac electrophysiology has always involved a balance between depth and scale. Action potential recordings provide rich mechanistic information, while MEA gives us scalable, label-free measurements from cardiomyocytes and 𝘁𝗵𝗶𝗀. LEAP is designed to bring those advantages closer together. Today, I'll introduce what LEAP is, how it works, and how it fits into the standard MEA workflow, and then show pharmacology examples where LEAP reveals expected changes in action potential morphology. To begin with, let's first see how different functional assays provide information about cardiomyocyte behavior. On one end of the spectrum, we have clinical ECGs. These give us a whole heart readout. On the other end of the spectrum, we have patch clamp, and this gives us a direct action potential measurement from a single isolated cell. MEA sits in a valuable middle position. It records from a functional cardiomyocytes in 𝘁𝗵𝗶𝗀. Cardiomyocyte MEA field potentials reflect the propagation of action potentials across a functional syncytium, similar in concept to how an ECG reflects electrical activity across the heart. That makes MEA a powerful platform for scalable cardiac electrophysiology. We can look at the functional activity across many wells in a label-free format from intact cardiomyocyte monolayers. However, as I mentioned, patch clamping provides valuable insight into cardiomyocyte behavior. Cardiomyocyte behavior is the result of the complex interplay of different ion channels opening and closing at different times, and each channel contributes to a specific aspect of the action potential. The upstroke, or the depolarization phase, is predominantly driven by sodium currents. This plateau phase that follows afterwards is strongly influenced by calcium currents. And finally, repolarization is primarily governed by potassium currents. This is why action potential morphology is valuable. When a compound affects sodium, calcium, or potassium channels, those effects often show up in different regions of the waveform. So when we measure the action potential shape and gain insight not only about whether the cells are beating, but also how the underlying electrophysiology is changing. So as we just saw, patch clamp data provides rich electrophysiological detail. It is the gold standard for measuring membrane potential at the single-cell level, and it gives direct access to the action potential waveform. But it is lower throughput and requires more technical expertise. MEA field potentials, on the other hand, are scalable, label-free, and well-suited for functional screening. They measure population-level behavior from cardiomyocyte monolayers and are much easier to deploy across multi-well experiments. The key point here is that neither approach is better. They each bring distinct strengths, and they each answer different questions. So an ideal compromise in this situation would be to develop an assay which takes the best of both worlds. And that particular assay is the LEAP assay. The LEAP assay offers more waveform-level information in a scalable MEA workflow. LEAP builds on the strengths of MEA by enabling action potential waveforms from the same cardiomyocyte assay. With LEAP, researchers can maintain MEA scalability and throughput, preserve label-free recording, and add action potential like morphology. In other words, LEAP helps bring together the two things researchers want: the mechanistic detail associated with action potential waveforms and the scalability of MEA. That's why we often describe LEAP as adding waveform depth without giving up MEA scale. Now that we've established a solid foundation of the importance and utility of studying the cardiac action potential, let's now delve deeper into the details of the LEAP assay. First, we'll define what LEAP is and how it works. Then, we'll talk about how LEAP fits into the standard MEA workflow. And finally, we will look at example pharmacology data showing how LEAP captures expected changes in action potential morphology. First, let's delve into the technical overview: what LEAP is, what changes during LEAP induction, and why the resulting signal gives us more action potential information from the MEA platform. LEAP stands for Local Extracellular Action Potential. It is a unique capability exclusive to Axion MEA systems. At a high level, LEAP is an MEA recording mode that captures action potential-like waveforms from intact cardiomyocyte monolayers. The key point here is that this assay can be performed using the same cells, the same MEA plate, and the same Axion workflow. We're not moving to a separate platform, we're not switching to a completely different assay. We use the same setup to record a signal that more closely resembles the cardiac action potential. So how does the LEAP assay actually work? The answer lies in the cell-electrode coupling, and this is the key idea behind LEAP. In a traditional field potential recording, the electrode measures electrical activity from the cardiomyocyte syncytium, but the signal has a field potential-like shape. During LEAP induction, coupling between the cardiomyocyte syncytium and the electrode is enhanced. As that coupling improves, the recorded signal changes from a field potential-like waveform to an action potential-like waveform. So LEAP is not changing the fundamental biology of the cells. It is merely changing the recording relationship between the cells and the electrode, allowing the electrode to capture a deeper signal. This slide shows the transformation clearly. Before induction, we see the field potential signal. After LEAP induction, the signal increases in amplitude and changes shape to resemble a cardiac action potential, with clear depolarization, plateau, and repolarization phases. This is where the power of the LEAP signal lies. Once we see the action potential waveform, we can quantify features such as APD 30, 50, and 90, and other morphology-based endpoints. This is not replacing the field potential, it's simply adding another layer of information from the same MEA platform. So, a question that naturally arises is whether LEAP induction alters the behavior of cardiomyocytes, and the answer to this particular question is no. As we can see in the example below, LEAP is induced on selected electrodes, while neighboring electrodes remain in field potential recording mode. When we compare the neighboring electrode before and after LEAP induction, the field potential shape remains stable, and the beat period remains consistent. This tells us that LEAP induction is localized to the selected electrodes and does not disrupt the broader cardiac behavior of the syncytium. Now, this is an important confidence point. The LEAP assay adds a deeper waveform readout without fundamentally perturbing the assay. Now that we've covered what LEAP is, let's move on to how it can be incorporated into the experimental workflow. The LEAP assay fits seamlessly into the standard MEA workflow for multiple reasons. First, it uses the same MEA plates. There is no special plate or plating protocol that is needed to record from LEAP signals. Second, LEAP induction is software guided. It is a simple push-button workflow, and the induction step takes approximately 10 minutes. Third, LEAP gives you flexible electrode selection. You can induce selected electrodes or subsets of electrodes depending on your experimental design. And fourth, as we just saw, LEAP induction is localized and does not disrupt surrounding field potential activity or beat period. So the overall message is this. LEAP adds a deeper waveform readout while keeping the experiment familiar, flexible, and scalable. To fully illustrate how LEAP fits into the MEA workflow, let's first look at a typical MEA workflow. End users plate cardiomyocytes on the MEA plate, record baseline field potentials, add compounds and allow the cells to equilibrate, and then record dosed field potentials. This standard workflow already gives researchers a scalable, label-free way to measure cardiac electrophysiology. LEAP builds from this same foundation. It is an additional recording capability that can be added depending on the goals of the experiment. Now, there are a few ways to incorporate LEAP. In a LEAP-focused workflow, you can induce LEAP on a subset of electrodes and record a baseline LEAP signal. After compound addition and equilibration, you can induce a different subset of electrodes and record the post-dose LEAP signal. Alternatively, in an MEA plus LEAP workflow, you can run your standard field potential assay first, and then apply LEAP after compound equilibration to add action potential-like information at the end of the experiment. This flexibility is useful because it lets the researcher decide how much of the electrode array to preserve for their field potential recording and how much to allocate for LEAP. The key practical point is that LEAP can be added without rebuilding the assay. Now we've established how easily the LEAP assay can be run, either in isolation or in conjunction with standard MEA assays. However, there are some finer details which can help end users maximize their chances of recording high-quality LEAP signals. First, we have to choose the right plate. Biocircuit MEA plates are recommended for the highest LEAP induction rates, and the right plate format should be selected based on how many electrodes per well are needed for the experiment. Second, the experimenter should start with strong field potential activity. Healthy, consistent baseline field potentials are the best starting point for successful LEAP recordings. This means that the fundamentals of MEA recording still matter, using the recommended coating, plating density, maturation time, and media conditions for the cardiomyocyte model. Good LEAP data starts with good cell health and good baseline MEA activity. For studies that require multiple LEAP recordings over time, plan electrode usage in advance. Because LEAP signals typically last at least 10 minutes, and because it can be difficult to re-induce LEAP on the same electrode after the signal reverts, it is often best to induce LEAP on subsets of electrodes rather than all electrodes at once. LEAP is also compatible with electrical and optical stimulation, which is important for studies where pacing or rate-dependent effects matter. Finally, we need to match the analysis endpoint to the biology. APD90 is useful for repolarization timing. Rise time can help evaluate depolarization-related effects. Triangulation captures waveform shape changes. And EAD detection supports arrhythmia risk assessment. Now we'll move on to the pharmacology section. We've covered what LEAP is and how it fits into the workflow. The next question is whether LEAP captures expected biological responses where cardiomyocytes are treated with compounds that affect different ion channel mechanisms. To evaluate LEAP performance, cardiomyocytes were treated with compounds treating different ion channel mechanisms. The goal is to show that LEAP captures expected changes in action potential morphology. We'll look at examples that affect calcium, potassium, and more complex electrophysiology. As we go through the data, pay attention to not only whether the waveform gets longer or shorter, but where in the waveform this particular change occurs. Before looking at compounds, here are some key metrics that LEAP is able to measure. For depolarization, we can look at rise time. For repolarization, we can look at APD 30, 50, or 90. We can also evaluate triangulation, which reflects changes in the shape and slope of repolarization, and arrhythmic events such as early after depolarizations. These are exactly the kinds of features that make action potential morphology so valuable. LEAP brings those measurements into the MEA workflow. Our first example that we will look at is nifedipine, an L-type calcium channel blocker. If you recall from earlier, calcium currents strongly influence the plateau phase of the cardiac action potential. Therefore, we can expect a calcium channel blocker to shorten the action potential waveform. And this is precisely what we see here. Nifedipine produces a dose-dependent shortening of the LEAP waveform, reflected by reductions in APD 90 as well as APD 30 and APD 50. This example shows how LEAP can capture expected electrophysiology in a clear, quantifiable manner. We can also take a look at prolonging repolarization. A good compound to illustrate this effect is E4031, a hERG channel blocker. hERG channels contribute to repolarizing potassium currents, and blocking hERG channels is expected to prolong repolarization. In the LEAP signal, we observe this prolongation directly in the waveform. At higher doses, we also see early after depolarizations. An interesting thing to note here is that the prolongation occurs after the plateau phase, so we only observe this in the APD 90. All of this contribute to why LEAP is so valuable. It does not just tell us that repolarization changed, it lets us see how it changed and whether arrhythmic events emerge as the waveform becomes unstable. Now, this slide compares field potential and LEAP views of the same type of event. Field potentials remain a powerful readout, but certain features can be subtle. In LEAP, those features become much more visually apparent. You'll notice the scale bars. LEAP signals are often an order of magnitude larger than field potentials while still maintaining small noise profiles. This means that depolarization, repolarization, and EAD features are clearer in the LEAP waveform, making them easier to identify, measure, and support with automated analysis. That is an important benefit for screening and repeatable analysis. LEAP helps turn complex waveform behavior into more accessible, quantifiable endpoints. The next example highlights why action potential shape matters, not just action potential duration. Tolterodine and pterodylene were developed for the same indication, but they had very different clinical outcomes. Tolterodine had a clinically clean profile, where pterodylene was withdrawn due to torsades de pointes risk. Patch clamp recording showed an important difference in action potential morphology. Tolterodine prolonged the action potential without major triangulation. Pterodylene, in contrast, induced pronounced triangulation of repolarization. This is a strong example because it shows that waveform shape can reveal risk beyond duration alone. So, here we see the same compounds using LEAP. The LEAP recordings showed the key distinction observed in the patch clamp benchmark. Tolterodine shows APD prolongation with relatively preserved waveform shape. Pterodylene shows clear triangulation of repolarization at higher concentrations. This is where the LEAP becomes especially compelling. It is not just producing a waveform that looks like an action potential, it is capturing biologically meaningful morphology changes that align with established action potential findings, and it does so in a scalable MEA workflow. So why add LEAP to your cardiac MEA assay? LEAP provides detailed action potential morphology. It gives large, robust signals with strong signal-to-noise. It is scalable and easy to use, and it is non-destructive and label-free. The main take-home message is this: LEAP adds waveform depth without giving up MEA scale. This means that researchers can continue to rely on the strengths of MEA while adding a deeper layer of action potential insight where morphology matters. Before we close, I want to take a step back. LEAP is a powerful cardiac assay, but it is one part of the broader Axion MEA cardiac toolkit. On the same platform, researchers can evaluate electrophysiology, contractility, and propagation. This means that you are not limited to one view of cardiac function. The same Axion MEA platform supports multiple scalable, multi-well label-free cardiac assays. The workflow is integrated, allowing researchers to run complementary assays with ease, and the result is stronger data and deeper insight, from discovery through safety assessment. So the value of LEAP is not only that it adds action potential morphology, it also fits into a broader platform designed to help researchers understand cardiac function more completely. To learn more, visit us at axionbio.com or reach out directly to continue the conversation. I would be happy to share additional datasets or discuss how Axion MEA could integrate into your specific discovery program. Thank you very much for your time.